morning, good afternoon, wherever you may be in the lab. Thank you so much for making chemistry part of your day. So I think the procedure itself in this lab is straightforward enough. I don't actually need to demonstrate on video. You're going to get the wells that are in front of you in the laboratory, and you're going to put a number of drops in each. The number doesn't really matter, it's equal amounts. So whatever the lab says, or you want to just put 10 drops and 10 drops, something like that, or 7 drops. It's really not that important, but you put drops of each aliquot on the grid. And here's the key part. Then wait a while. Come over and do what I'm going to talk about here. So fill out the grid, let all the drops fall, take a quick glance to make sure there's no observations to be noted that might go away, like bubbles. But anything short of bubbles or a flash of light, you can just wait. So take a quick check, make sure there's nothing immediate happening, and then let those sit and settle. And it's going to make it a lot easier to make observations if you wait a little bit. So what are you going to do while you wait? We'll get our notebook set up. So same as always, fill in your headers, title of the lab, lab partner, date, those kind of things. For the procedure, just put a statement that you followed the provided handout. I will talk about safety at the beginning of every single lab, so summarize what was said there to make sure that you paid attention and you're being safe in lab. And then for the data today, so I'm going to change this up a little bit from what the lab asked you about. It's saying to mix solutions and see if there's a reaction, and then describe what occurs. But if you can't describe a procedure unless you describe the before and the after. Otherwise, you don't know if something happened. If you take a blue solution and it stays blue, nothing happened. But if you had a clear solution, pour it together and it turns blue, something happened. So you can't just say blue solution reaction or blue solution no reaction. We need to know where we came from to see if anything changed. So what I want you to do is write those initial observations. So we have 10 chemicals labeled in your lab 1, 2, 3, 4, 5, 6, A, B, C, D. So take those 1, 2, 3, 4, 5, 6, A, B, C, D, put 10 lines on your lab, and write down what those 10 chemicals are. Then I want you to do two things. One is for your own benefit to make this lab way easier, and the other is because we need to have those observations. So the first thing I want you to do is, as I say, cut the head off, identify your cation, identify your anion. So remember, if you cut something like Na2CO3, sodium carbonate, hopefully when you take that first element off, realize that 2 subscript is not a polyatomic ion you've memorized. It means you have 2 NAs. So our actual cation is Na, and our anion, now there's 2 capital letters, so we keep the whole thing together, so that is a polyatomic CO3. Now hopefully you've memorized CO3 has a charge of 2-, and you can go to our old friend the periodic table and look in column 1 and see that sodium is there. It's in group 1, so it's a +1 charge, and you have the identity of our cation, the identity of our anion. I've left off the amounts, but there's 2 sodiums to balance out the 1 carbonate, and that's why the 2 is there. So do that for all 10 chemicals. Get your 10 cations, 10 anions, have that listed. That's going to make your life way easier later on. But then the other thing is I want you to describe what it is. So anytime you're describing a material, there's really 3 things, at least 3 things you can describe. One is the clarity of it. Is it clear? Is it cloudy? Is it foggy? That kind of idea. The color, and colorless is a color, right? Kool-Aid is clear, but it can also be colored, or Gatorade. You can have red Gatorade. That's a clear solution, but it's red colored. And water is clear and colorless, so depending on, so sodium carbonate in this case would be clear and colorless. And then write down the phase of matter. It's a liquid, it's a solid, it's a gas, I don't know, it's a plasma, whatever else you might have in there. So clear, colorless, liquid. Clear, blue, liquid, whatever it happens to be. Write that down. So you should always be able to tell the clarity, the color, and the phase of the matter you're looking at. So put all those observations in, and that'll be your first part of data. And the second part of data, basically, I want you to do exactly what the book says. Build this grid, 1, 2, 3, 4, 5, 6, A, B, C, D. That's where you put all your drops in. Come back to your plate, and let's put your observations. If nothing happened, if you have a clear colorless liquid, mix with a clear colorless liquid, and you make a clear colorless liquid, just put an X there. And then I put a little key at the bottom. X means no observable change. Just because we don't see a change doesn't mean a reaction didn't occur. Just like I've never seen a leprechaun, I still know leprechauns are all over Ireland. I just haven't been to Ireland yet. Jokes aside, if nothing's observed, nothing observed. Doesn't mean nothing happened. We could have missed it. It could be at a microscopic level. And there's other things, right? There could be a temperature change when we mix. There's a lot of things that could go on that would indicate a reaction other than just changing the clarity of it. But let's say I have one where the solid stays mixed up with the liquid. It might look like milk, and it's cloudy white mixture, I might call that. Or one where that white powder settles to the bottom, because I took my time figuring out how to identify all my cations and anions, so everything settled nicely. It was easy to observe. And then I could see that the liquid above was a clear colorless liquid with a white solid precipitate on the bottom. So if you can see two things, describe the two things. Now, if they're totally suspended and you only have one thing, then describe one thing. But that's the idea of letting it sit for a little while, so you can do that. Fill in this graph or grid, and then everywhere where you have a precipitate, a solid, not a reaction, but a solid, I want you to identify what the solid is for the conclusion. So again, I'm modifying greatly the lab, but that's all I want you to do. So in my well here, A2, I might have, okay, so I have cloudy, that means there's a solid in there, so I need to identify that precipitate. Now I don't have the things up here, but general rule of thumb with solubility, and I hope this lab demonstrates it really nicely to you, is things with a +1 or -1 charge tend to be pretty soluble. Anything with a larger charge, +2, -2, +3, -3, they tend to be really insoluble. So small charges tend to stay in solution, large charges pair up and fall out of solution, and hopefully you'll demonstrate that in lab today. So, if you have these things and you're trying to guess a precipitate here, guess what? It's going to be the carbonate because it's a bigger charge than the sodium. And you can just take the biggest charge, the biggest positive and the biggest negative charge between A and 2, put those together, and you might get something like iron FeSCN. Now this is a 3+ charge, this is -1, so when you cross them down, you might get FeSCN3, and I might call that iron 3 thiocyanate. Again, this will give us a little bit of practice with our nomenclature, our naming, and a lot of different skills we've been using in class. So that's the general idea. Give me a list of the precipitates from the grid, and then I want, for your conclusion as well, I also want list the cations and anions that tended to stay in solution. These are, again, going to be the ones with the smaller charge. And give me the cations and anions that typically form precipitates. These are going to be so the precipitating ions will be the ones that with the larger charge. The ones that stay in solution will be the smaller charge. But you'll be able to see this. You have your list of precipitates. You're like, oh, look at that, Fe, 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 Fe. That tends to form precipitates. There's no NAs anywhere on my list. That tends to stay in solution. So summarize that so we can actually have some kind of conclusion out of this lab. And that's it. I think it's pretty straightforward. Thank you for your time, attention, energy. Have a wonderful day.